Hi, I'm Jay, a visiting researcher at UIUC, and I'm doing my PhD from SUTT Singapore. I would like to introduce our research, EarSense, which was conceptualized with the vision of exploiting teeth as an activity sensor. EarSense is based on the premise that vibration generated from human teeth would conduct through the jaw and skull bones, and eventually arrive at the eardrum. This paper asks two questions. One, can today's off-the-shelf earphones be used to pick up the vibration signals? And two, can we analyze these vibrations and infer the accents or gestures of the teeth and even the teeth locations where such gestures were made? Before describing details, an obvious question arises. Why should we care? We envision a wide range of applications, ranging from healthcare to user interfaces. Consider the case of seizures. Today, patients go out with trained dogs that can alert the patient before the onset of a seizure. However, it has been observed that teeth chattering precedes a seizure. EarSense might be able to detect this teeth activity and alert the patient. EarSense may also be used in remote dental monitoring, where vibration data from the teeth can be uploaded for clinical analysis. In factories or hospitals where workers are wearing gloves or have their hands full, EarSense can be used to perform simple actions or send simple commands. EarSense may also be helpful even in everyday use. A person could type in a PIN number on her phone or click and scroll while wearing a gloves in the winter. Finally, EarSense can help accessibility, such as by replacing the Android switch, which today has to be bought as a separate accessory. Importantly, gestures through earphones would be privacy preserving, support contactless and hand-free sort interactions, and also enhance the usability. So, what makes EarSense possible? Our first pillar is based on the exploitation that commercial off-the-shelf earphones speakers can be programmed as a vibration sensor. The idea is based on the very basic principle of electromagnetic duality. If diagrams of a speakers are vibrated through external force, electrical signals are generated in both the channels. Building on this phenomena, we intend to repurpose the earphone as a vibration microphone. In other words, the speaker can act like a microphone and hence can sense vibrations that conduct through the face and skull. But the system in practice would require an automated toggling between the two. And we can do that. We do on the fly toggling, which is to and fro conversion of speakers to microphones using software based jack retasking of pins. Basically, pin 14 to 17 of Realtek audio codec chips were programmed to act as a microphone if there is no sound being played. Having captured the signals at two channels, let's study feasibility of using stereo signals for inferring teeth gestures and locations. EarSense records three types of teeth gestures across 7 locations. These include 3 locations of tap, left, middle, and right, 2 horizontal slides, left to right, and vice versa, and 2 vertical slides, up to down, and vice versa. An example of left tap is shown in the animation. For EarSense, the teeth gesture inference is a 3-step process. First, we detect if there is actually a teeth-related activity. This classification is based on frequency domain analysis and a study of harmonics. Once we are sure of a teeth activity, we estimate if it is a tap or a slide. The classification between tap and slide is based on analysis of spectral features, template correlations, and signal durations. Taps are impulsive, hence they create a wider band of signal. If a tap is detected, we proceed with its localization. The challenge here is that teeth behaves as a dispersive medium. Vibration signals of different frequencies travel at different speed. Hence, left and right channels are not delayed versions of each other. The standard delay analysis will not suffice here. We designed a threefold approach to find relative locations of the tap. We propose to use differences in zero crossing time at left and right channels, dominance of cheek wave energies, and time difference of lower frequencies. We exploit a differentiating opportunity for tracking slides. As can be seen in the animation, the location of friction shifts during a slide. Hence, we designed a delay profile-based classifier to identify among the four slides. The delay changes magnitude and sign as the slide progresses. So we have proposed a processing chain which is not only accurate but scalable as well. It proves to be robust against external interferences like walking, cooking, cycling, and nodding. To conclude, this paper claims that we can use off-the-shelf earphones to sense facial surface vibrations. These vibration signals can give idea about teeth gestures and even the locations of corresponding activity. We request to have a look at our paper for further details. We will be very glad to discuss and push this rapidly evolving field around hearable computing. Thank you.